So to finish up our lab about energy modes, we also need to solve the following problem. As you can see here, the output of the console is hello world, but then instead of exclamation mark and new line, some weird symbols are being sent, 0, 1, and R. Okay, something's not working correctly there. And actually, the explanation is pretty simple. And it's the following. UART, peripheral, through which we send this hello world text, is a high frequency peripheral, which is clocking from the same clock signal that the CPU is clocking. And when we say the CPU to turn off its clock and go to sleep, to turn off high frequency clock, then the clock signal is lost also for the UART peripheral. Let's check it out in the datasheet. So in Adobe, the user guide, reference manual, Leopard Gecko, and let's go to clock management unit. So in this picture, we can see that we are using, I guess, UART 0, timer 1, high frequency peripheral clock. So UART, I don't think it's visible here, but UARTs are high frequency peripherals. They are somewhere here between the timers and I2C, and they all clock from high frequency oscillators. And when we tell the CPU to go to sleep and switch off the oscillator, these peripherals also get frozen. Basically, they are paused, they are suspended, and as a result, in our code, when we send this hello world text and then go to sleep, the first letters are being sent, but the last letters are not sent because this UART has 2-level buffer, which means that you can send one byte and hold the next byte in the buffer, so you can send them faster. And when each letter is sent, basically the UART receives 2 bytes. One is sending and one is waiting. When it's complete, then it accepts the next byte and sends it. So basically, the first letters, hello world, are being sent, but the last 2 letters, when this print returns, they are still in the buffer, and we put the CPU to sleep, and they are not sent correctly. The processor starts to send them, but then it's shut down, it's paused, it's put to sleep, suspended, and these last 2 letters are not sent. This is why you see that hello world is sent, but the last letters are being sent wrong. So after waking the CPU up, it resumes sending, but the data on the lines is already corrupt. So the thing that we have to do is pretty simple. Before going to sleep, we just need to wait for UART to finish sending. How we can do it? In our print.c driver, we have this USART TX, and what this USART TX does is it has this while USART is sending, wait, and when it finishes sending, then send the next byte. So we could do 2 things. We could either first send the byte and then wait until it completes, or we just copy this line and paste it before entering sleep. And for USART, we will use the same UART that we were using in this print.c, and it is UART 0. So here I would type UART 0 status. So while UART 0 status and USART status TX buffer low is not set, we wait. So basically, and also I can delete these curly braces and add semicolon. So basically this thing simply waits for UART0 to finish sending this, these two last bytes, and only then it puts the processor to sleep. However, okay, actually this code will work, but there's a little bit caveat. If you haven't sent any bytes yet and you call this thing, then the processor hangs because the TX buffer never gets low if it was never filled. So the correct thing to do for safety reasons would be in our print library, at the end, we add something like printf. Actually, I will demonstrate it to you through an example. The problem is, I think it's like a bad thing for this UART that it doesn't have such thing, but the TX buffer low is set only after you have sent some bytes. So if you haven't sent any bytes, then the processor hangs on this line. And if we have sent something, it will not hang. So it is best to just send some dummy text after print init, sending some dummy text using printf, something like hello, new line. This will actually prevent this problem. So initialize, send hello, and only then you can check for TX buffer to be low. This is just technicality for this processor. But anyway, now let's build it this way. So we have added this one line to our code and also this print hello after print init. And now I will upload it, flash to device, program, and let's clear it. There's still some problem. I don't know why. Let's see, maybe there's a wrong flag. 1 second. Okay, so yeah, we should use a different flag. So let's go to the datasheet of this processor and let's check out UART. Actually, it will use the same registers as USART, so let's go there. And there should be something like status register. And we need to find the correct flag between these, which will be set or cleared when the buffer is, for example, empty. So let's check out. We could use TXC. So when transmission has completed and no more data is available in transmit buffer and shift register, this flag is set. So when it has sent both the buffer value and the actively sent value, then this flag is set. So basically what we can write here, TXC. So basically the program waits until UART status and UART status TX complete becomes 1. So I build it. Previously, it only waited for the buffer to get empty, but that's not what we need. We need more. When buffer is empty and also shift register in UART, the data being sent online actively is also done. And as you can see now, this thing prints correctly. And also, let's go to energy profiler and check out if it's also low energy. So, and in this energy profiler, I can see that when the processor sleeps, it still consumes very small energy. So let's zoom in, for example, one period. Okay, so the processor is sleeping. Then after 1 second, an interrupt happens. Yeah, it's pretty precisely 1 second. And interrupt happens. The LED is toggled to the opposite state. And also this hello world text is sent out. And the program waits until the text sending is complete, and only then it goes to sleep. And after 1 second happens the same thing. Okay, also let's check out this part in particular. Using this energy profiler, we can detect very small changes in power. So we can see, okay, this processor was sleeping, then it woke up, and then it went to sleep. So we can evaluate, how good our code is by looking at how long the CPU is on. Well, for example, in this case, I don't know, it's maximum zoom. Um, so from peak to peak, what the hell? So the processor is on about 1.3 milliseconds. So let's check out if it's good or bad, a lot or a little. Um, hmm, 1.3 milliseconds. So the only things that the processor does is it says hello world, and the exclamation mark in new line, and then goes to sleep. And also the interrupt service routine is executed. Interrupt service routine takes, some like 100 clocks to perform. It enters the interrupt service routine, then does something and goes out. Um, but what about this text? So how long do we need to send this text out? You see, in our serial communication, in settings, we can see that we're using speed 115.200. It's bits per second plus a start bit and a stop bit. So it's actually 10 bits per 8 bits that we send, because in the beginning there's a start bit and at the end is a stop bit. So the time for each bit is 1 divided by 115.200 is this much, and we multiply it by 10, and this is the time that the CPU spends to send each letter. And how many letters do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 letters. So 14. We multiply this time by 14, and we arrive at this number, 1.2 milliseconds. So as you can see, the CPU actually spent most of the time, most of these 1.3 milliseconds, simply by sending this text. This is just something that you need to remember. Sending text, even though the speed seems very, very big, 115,200 bits per second, even this short text actually takes 1.2 milliseconds to be sent, and actually most of the time the CPU is spending sending this text, right? So if you want to save a lot of power in microcontroller programming, you actually want to, send as short text as possible. Maybe you want to disable text sending altogether, for example. And maybe you want to send the text out only if some button is pressed. You hold down the button and you get the log out. And if you release the button, then the processor doesn't send anything and goes to sleep immediately, something like that. You would save a lot of power, because servicing interrupt was really fast. Going to sleep also very fast, but most of the time was spent sending this text, right? Mm, the only thing that we can check out in the data sheet somewhere, it says here, maybe under clock management unit, that when the clock goes to sleep, when high frequency peripheral clock goes to sleep and then wakes up, it takes something like 2 microseconds for wake up. I don't remember, it was written somewhere here. So it takes a little bit of time for the microcontroller to start up from sleep, or milliseconds. Let's see, 2 ms. Maybe it finds something. But generally, the putting processor to sleep and making it up takes some time, but it's not that much. But anyway, this is how we can use energy profiler to also measure the time. Maybe it's somewhere here, to measure the time between, waking up and going to sleep. And this way we can evaluate how good our code is. So this code's pretty good, except sending some data, it pretty much works. Okay, let's end the session now. And let's see. So this is one thing which was like a little bit negative consequence of putting the processor to sleep. We have to remember that we have to add one extra line for our UART driver, that before going to sleep, we want to wait for the last character of UART to be transmitted. And sometimes people even make a separate library where they define function, processor go to sleep, and inside of that function, they wait for UART to complete sending, they wait for I2C to complete sending data and maybe something else, and only then they put the processor to sleep so that it is not in the main code. But in our case, in our simple example, it's in main code and it doesn't matter. It doesn't bother us that much. Okay, so enter AM2. Let's look at another consequence of putting processor to sleep. As I mentioned before, timer uh, also runs from CPU clock. So let's say we turn LED 0 auto pulse on, LED 0 auto pulse on, and we expect that the LED will be pulsing. So let's check it out. Will it pulse or not? Let's build this thing and flash it to our processor. So the LED number 0, unfortunately, it doesn't look like it's pulsing at all. Because, well, maybe it will turn on very, very, very slowly. But the problem here is that, oh yeah, you saw it actually started to blink. But the idea is the following. I'll draw it in Paint. So the timer runs and creates this pulse width modulation signal. So sometimes the LED, when it's when it's blinking, we set the brightness, for example, 50%. The timer, counts from 0 to 100, and it keeps the pin low, and then it sets high at 50, and it keeps high, and then sets to 0 at 100 and overflows to 0 and so on. And the thing is that when you stop the high frequency peripheral clock, then the timer is also stopped. And if you stop the timer at the moment when the output was low, then the LED is not shining. And if you stop the clock when timer 3 was outputting high level, then the LED shines all the time. So it's a little bit like randomness, at which point you will pause the CPU. If you pause it when the output was low, it stays low. And if you pause it when the output was high, then it will be high on 100%, right? Because this timer 3 is, being paused all the time. It runs in a step with the microcontroller's CPU. And when you pause the CPU, this clock is also paused, and at what point it will be paused, at this point or this point or this point, nobody knows. It's kind of random. So sometimes the LED is on and sometimes it's off. Right now it's more off than on because its brightness is set to low level. So it's a bigger chance to hit it when it's low than when it's high. However, with each overflow, the brightness is increased, so the width is higher, and at some point, it will be bigger chance to hit it when it's high than when it's low, so it's very inconsistent. So you just have to remember that high frequency peripheral items are paused together with the CPU, they are suspended, and they keep the state that they had right before suspending them. So if UART line was low and you stop the CPU, it stays low. If LED line was low and you pause the CPU, it stays low. If it was set high, it stays high. So you cannot use LED pulsations with low energy modes. It's impossible, at least for this CPU. There are some CPUs in which real-time clock um, can also output low frequency pulse width modulation signal. But as far as I know, most CPUs don't support such thing, and these real-time counters don't have um, an output pin for PWM. There is this low energy timer, which maybe can do it. But unfortunately, it more looks like it's a 16-bit down counter. And I'm not sure if it's not too much tied up with a real-time clock. So maybe it works, maybe it doesn't work that way. But these regular timers, they're high frequency and they're suspended automatically together with the CPU, so they don't work in this way. However, if we are talking about battery powered devices, we don't want to blink or pulsate LEDs from battery because LEDs consume little energy, but the battery is also very small. So little energy will drain small battery just as quickly as big energy source like in big light to a bigger battery. So it doesn't matter. So generally, before going to sleep, we want to switch off all LEDs. We don't care. We just want to switch them off. Um, and not have them turned on. So you can upgrade your code. Let's delete this LED 0. Let's instead switch the LED 0 off. LED underscore off, LED 0. We want to switch it off to save energy. So add this one line to your code, recompile, upload it, and check out the output from UART. Check out the energy consumption. You should see that it consumes really only a couple of microamps. And then upload the code to Ortus so that I can see that you actually did this lab work. Okay, and don't forget, check out the period of LED blinking when you are sourcing it from low frequency RCO. That's like 2 things that you need to do. Okay, so that's all for this lab. I will be waiting for your reports.